Welcome all. We started. Everything is ready. Yeah, let's get started. This is lecture session 12 for the live interaction session for the course of gas dynamics, fundamentals and application. And I am the teaching assistant who has been conducting live interaction sessions for the course. So today is the session 12. We'll be looking at MOC, specifically minimum length nozzle design. And that is a good uh, illustration to go about this MOC method. Uh, no need to introduce myself. In the last lecture, these things we'll look at if we'll get some time. We'll look at some the revision or something. But today, precisely, we're going to look at uh, method of characteristics, and let's get started with it. I'm not going to discuss things which are uh, fundamental today, but going to discuss fundamentals or some derivations of stuff. I'm hoping that we start with some prerequisites. We'll review them and then we'll use them uh, uh, as we move forward. Okay, so before that, let's also discuss the game plan. Before that, let's discuss the game plan as well. What are we going to do today? Uh, so the plan is of this sorts. Right. The plan is of this sorts. Just give me a second. Just give this mobile to go forward. Great. So I think sharing has stopped. Let me reshare. Okay. So what are we gonna do today? We're gonna demonstrate uh, use of MOC. MOC is method of characteristics to design a minimum length nozzle. What is the idea there? The idea is that um, in this minimum length nozzle, uh, there are gonna be a 2D flow, and we are gonna consider that. And as the flow expands, there will be Prandtl-Meyer expansion waves in a minimum length uh, in a minimum length nozzle, you find simple regions. Now, what simple are is uh, so there is a simple region, there is a non-simple region also in the nozzle, but the design itself is governed by technique. It's a simple implementation of MOC. So we are going to look at it and using that, and we're going to code it. We're going to write a code for it. Hopefully, we'll finish the code in the entirety of the session. Otherwise, and so let me show you what exactly do I mean by that. What are we going to look at is um, something of this sorts. Yes. So something of this sorts. So given a mark number, we want given so that's setting is of this sorts. Let's look at the setting. So there is a nozzle symbol would be request. So let's say there is a nozzle of some shape. Okay. And so well, I've not drawn the nozzle very fine, but the thing is that we are given that there is a sonic flow at the entry. The flow is sonic. And we want to expand that flow to some mark number, and that would be given to us. So just don't focus too much on the shape of the nozzle. Just uh, just take it as an system where you have some sonic flow at the inlet, and you want to expand it. That's the idea, and we want to use a minimum length. We want to design a minimum length nozzle. Now, when I said minimum design it, what do I mean? I just mean qualitatively, not qualitatively, non-dimensionally, the shape of it. And the size itself will depend on how much the flow rate is and other things. But essentially, how the shape would look like. And again, for a perfect idea, calorically perfect gas, you're gonna look thermally perfect gas. You're gonna look something of that sort. But to start off with that, let's review a couple of things. Let me see what else, what all we will need uh, to write this code. So let's review MOC. So let's write MOC. Let's review it. Uh, Characteristics. Okay, let's review this. So now uh, let me put out some materials. Let me put out some material for this. What uh, what do we need? Let me see. A couple of things from the chapter itself. Then uh, I'm not gonna waste a lot of time. Just deriving of whatever there is in this. So now we know. Just give me a second. Yeah. So let's get started. What I was saying was, yeah, the first thing is, let's look at, yeah, this is the first graph I want us to discuss or review further at least couple of things. And we have looked at it before when we were looking at unsteady flows. Essentially, there is this first angle that we want to discuss is, I think it's called Mark angle. Uh, so this is called Mark angle. Uh, this is sine inverse 1 by m. Okay. Now, what does this mean? This means, locally speaking, the angle at which the characteristic lines are aligned with this they're aligned to, let's say, uh, so before that, let me also mention theta. What does theta imply? Theta is the angle at which the, locally speaking, it's the angle at which streamline flow is there. So it's actually tan inverse v by u. Okay. If we think, yes. So this is what it is. Locally speaking, there will be a streamline, and there is a coordinate system associated with our definitions. We are looking at Cartesian coordinates. So theta is the angle. Uh, Theta is the angle at which the streamline is aligned to the x-axis, whereas mu is the angle with respect to the streamline, with respect to the flow, locally flow. How are the characteristic lines aligned? Plus mu, so tan theta plus mu, there will be one characteristic line locally, and tan theta minus mu, there will be a second characteristic line defining the domain of, and these two characteristic line define the domain of dependence and domain of influence. So for the point A, the two characteristic lines demonstrate the domain of um, influence, but when they are drawn backwards in negative x towards negative x direction, you see it is this region from which the properties at A will get defined. So a domain of dependence, there's a dependence of on A, uh, and so the flow at A depends on this domain of dependence. So that is there. Again, characteristics lines are, as you move away, they will not necessarily be straight lines. They can be curved. So this mu line will change as you move away from, as you keep changing your x and y location with your point, you will see your mu values will change. Um, these two, this is the first result. Um, and okay, so this itself is a result of, so what essentially are we doing is that, um, if you look at it, um, once the flow is supersonic, once the flow is supersonic, I should have mentioned supersonic nozzle, but anyways, let's not delve into that. We are discussing supersonic nozzles. So to be precise, I should not have this part of it. So I should not have this part of it, and it should only be of this sorts. This is how the thing will look like. Yeah. So now, um, so there's only expansion that is going to happen. No, the compression that we are expecting out of it. Now the thing is, these positions, the local curvature of the characteristic lines is itself one result of method of characteristics. This is the step one of it. And so I'm just gonna write this. The important thing is that dy by dx of characteristic lines come out to be uh, tan theta minus plus mu. Okay, so there are two things important to it. We see that locally it depends on the Mach number, and again because and so it's basically the characteristic lines are only depending on the local Mach number. They're not depending. It's only that the streamline is also oriented with respect to x-axis that we are getting this theta. Otherwise, it's if you see as a streamline fitted coordinate system, it's only 10 plus minus 3. And it's minus plus mu. So that's also an important thing. So what we see is there are two characteristics lines. One moves towards if you face in the streamwise direction, you will see there is one characteristic line on your left and one is right. So one runs in the left direction, other runs in the right direction. So there is a left running line, and there is a right one, and there is a certain nomenclature associated with it. We will discuss that also. Now, note how uh, tan theta plus mu is the line that runs on the left of it, isn't it? So this is the reason. So it's demarcated as C plus, and the reason being um, that it is oriented by tan theta plus mu. To signify that that's an important thing, that it corresponds to tan theta plus mu plus mu. Okay. Now, just similarly, there is a negative, this right running line, and that we will denote by uh, this tan theta minus mu. Okay. So this is the first result that we will later on need. Um, Now let's move ahead, and so this comes actually if you look about it. If you look about it, you'll see that once you have your nature of equations you have. So what exactly do we have? So let's look at in a 2D flow. The equation you have is of this sorts. It's let me. That's partial u. So it's It can be written as del x by del y. Or what is it? This is fine. This is the governing equation. Once you have your supersonic flows associated with it, then the coefficients will be negative. There will be some negative there will be, let me think. So phi xy. Yeah, everything is fine. As I was saying, uh, wait. So this is del by del x. So I've written it down incorrectly. Let me correct this down. It should be del by x. And this um, should be what? Del u by del y. Either you can write it as del u by del y, or you can write it as del minus del v by del x, or something of that sort. So it's basically this cross derivative term. So we use this also. And because of the continuity, del u by del x, it's unsteady flow. Unsteady flow. Uh, we'll see that does not matter. You'll see that once you see that there is this along the characteristic lines, this this um, PD partial this PD partial differential equation. Partial differential equations can be converted to ordinary differential equations under certain conditions along a certain contour. In that contour, we see that this the determinant, we have to define the determinant. I'm not going into that. Gets into a numerator by denominator term, and we have a matrix. We have a determinant of two matrices that have to go to zero, and from that we get this relation. If numerator is put to zero, then you get this relation. But at the same time, you also have to put denominator as zero. And from that, you get the compatibility equations. And what are those compatibility equations is something that we want to write. From there, we get the Riemann invariant. So we see that along these characteristics lines, um, first of all, these characteristics lines exist in this supersonic flow. And then uh, there is a certain condition, there's a certain condition that is satisfied on these flows, and that is something of the sort. So let me write that. Um, so along C minus, you have theta plus, now you have a Prandtl-Meyer function coming in. Theta plus mu remains constant, is a constant, and we'll signify that as K minus. So K minus being the Riemann invariant corresponding to um, the right running characteristic, and there's also a left running characteristic C plus, and there it is theta minus. So we want to remember this. Now you see that mu is associated with the Prandtl-Meyer expansion, and we'll look at it. Okay. So what else do we need to talk about? So let's get started with this. Let's get started with this design process, the code. and then we'll see what exactly do we need. Okay, so let me also draw that curve for us. So let's begin with this. So before I actually get started, the way I have written this code, or we'll implement this code, is that there will be a center line. And because the flow is symmetric, we are going to draw a 2D nozzle, not a cylindrical nozzle. We are going to look at a 2D nozzle. There will be a center line, and that center line, the minimum length nozzle implies that as soon as you reach sonic conditions, so by some means you will be reaching sonic conditions, right? Some compression or some way you might be reaching sonic conditions. Let's say you have Rayleigh flow. There is a combustion chamber where you're creating sonic flow. From that from those situations, what you will do is for minimum length you have to create a sharp nozzle and a sharp corner which expands the flow in such a way that um, it expands to the design Mach number. So let's look at it. Right. Let's say this is the throat, and then let's say this is the throat, but then you simply create a sharp nozzle. That is what I wanted to. That's something of this sort is there. So wanted to imply sharpness, but maybe it's not very well portrayed. But first of all, the first thing is that we will assume that there is a sonic. This is the throat, and the flow. This line. Let me color this line as orange. This is the line at which our nozzle starts. This is the line called as sonic line. So I will write this also. This is our first assumption based on the way, see, this nozzle design has been looked at in the lectures also. I'm just repeating it and also trying to code it for us to see we don't miss out a step. Okay, so sonic line. Let's get this. So this is the sonic line. Again, not looking at the this one, not looking at what do you call the second half of it, because it is just symmetric. Just by virtue of symmetry, we are using that to get our way. Now with this, what happens is then the flow see the sharp corner. So you're gonna see some you're gonna see some branded wear expansion just from the nozzle. That is what is gonna happen. We're gonna see a series of branded wear expansions. Okay. Um, let's say of the sorts. Okay. At the same time, from the other half, there will be symmetric Prandtl-Meyer expansion waves that are gonna join. Because of the symmetry, what is gonna happen is they will appear like this. They will appear to reflect from the mid plane, and so there will be a series of reflected waves also that we are going to see. Okay. Now, how does the method of characteristics come in this one? That is what we are going to discuss. Okay. One more thing is, let me just draw this for you. So what we expect from this design of the nozzle is that first of all, C minus and C plus is something that we are going to discuss. Let's do that. But Anyways, what we expect is that at the end of the nozzle, the flow is again straight, so it's not two-dimensional. It again is in the primarily in the extraction. There is no v velocity, and there is a Mach number, Mach exit, that we are going to design the nozzle for, and the v is 0. Now, what does v equals to 0 implies? We are going to talk in these terms. Theta is 0. Okay, so this is what we expect. Now you see these Prandtl-Wiener expansion waves in themselves are actually characteristics lines, if you think about it, because these are the lines. Characteristics lines are what lines? These are the lines along which or disturbance propagates along these lines. You can think of in this manner. And so, what is exactly happening is that once the Prandtl-Wiener expansions happen, these corresponds to characteristics lines emerging from this throat point. Now, let's also do some nomenclature that we want to use later on. Uh, we will pick this as origin, the point at which the sonic line starts. I want to fit our coordinate system at this point, and this is the point which I am talking about. So this is the point. Now, and there's a throat corner just above that, um, and I'm naming it for meanwhile as A. This is the throat corner, and so once the flow starts expanding, what do you expect? Uh, if you look at it at this corner, um, the flow is going to expand. First of all, for the flow to turn in this direction, um, you need to disturb the flow, right? You need the flow to know that there is this region where you can expand it. Now, that can only happen if there are some characteristic lines that emerge from the throat corner and move towards the overflow or towards the center line, and they will inform the flow that once the flow approaches these characteristics lines, um, they will get to know that, oh, okay, there is some disturbance, and then they will change their shape, just like how in the Prandtl they will change their direction. So just like how in the Prandtl expansions we drew lines, what we expect is that there are going to be some series of the flow is this one. So if we think from the point of origin of these C minus these expansion waves, these lines are right running, right? These are right running extension waves. So I'm gonna color them in a certain manner. Let me color them by some. These are some C minus lines. Okay, I'm going to mark that there. So, so I'm going to say these are C minus lines. The reason is just the why we are calling it C minus lines, because these lines run from the throat origin to the throat corner to the center line, and that direction is actually uh, right running from the point of the other is the left lines. Um, these are what do you call? These are emerging from the other throat corner, from the on the other throat corner. This is the top throat corner. The bottom throat corner will inform the flow in towards it um, using C plus lines, right? So for that, I'm going to use this color. It's not a bright color, anyways. Okay. Now you see, the way to look at it is, um, the way to look at this thing is that, just give me a second to think about it. So, yeah. So the way to think about this is, uh, there are a series of C minus lines. There is a region. Okay, let us mark that region also. That would be also interesting. So there are particular regions which are character. There are three different regions. If you think about it, so this is called a characteristic mesh. What we have kind of drawn right now, and there is a certain region that we want to look. Well, we would like to look at. So if you look at this, if you look at this part of it. Like this color. So if I look at this part of it, so this is a distinctive region. Then there is also this region. Um, this is again a region. Let me color it differently. And then there is another this. Let me draw this region also. So if you see in the minimum, if you look at it, so there are three regions. Okay. Look at this region, the one which just starts with the sonic flow. There is no C positive lines, C plus lines which have emerged up yet. Okay. So now in this case, what exactly will happen is that this is primarily Prandtl-Meyer expansion. This is nothing but Prandtl-Meyer expansion. Um, so this is primarily Prandtl-Meyer expansion, and this can simply be solved without actually looking at these method of characteristics. So the flow in this region, this part of it, can be understood. Now, what demarcates or what marks the boundaries of this region is, first of all, there are a couple of things. So let me make a copy of this thing, and now let's only focus at this two region, this part. The first point is the point at which the first characteristic line reaches the center line. Okay. If you think about it, this will be very close to sonic line only. Once the flow is little bit also affected, is expanded a little bit, the first mark line, because mark lines, these Prandtl-Meyer lines or expansion waves, are our manifestations. We decide what mark this expansion wave we are going to look at. The first mark wave uh, is like the first you call this as the leading mark wave, brand expansion wave is up to us. We decide it. So, so numerically speaking, we'll have to decide first leading mark wave that we are going to resolve. Okay, so that is, and that line reaches the center line, and that is the first important point for us. So I'm going to call it as one. Now you see, from that there is this line reflects. This is a specular reflection. The angle at which it will what do you call it will attack or hit the center line. It is going to reflect the at the same angle. I have not drawn it like that, but it should be like that only. I've not drawn it in this diagram. It is not like that, but we'll remember that. Then there are a couple of points at which this C plus line is hitting the other original C minus lines. So again, other C minus lines are also our artifact. We are going to decide what series of C minus lines we are going to resolve our flow for. So that is something up to our hand. It's like discretizing our grid or space, discretizing our space into a grid. It's up to us at what grid points we want to uh, solve the flow for. At other grid points, we'll have to either find the grid or again redo the calculation for the other grid or so on. It's of that sort. But there will be certain points. And those certain points, what I'm going to do is I'm going to write it as 1, 2. The first point that reaches, that meets there. Then 1, 3 and 1, 4 like that. And so on. The last point is the point at which the flow has expanded to its highest mark wave. Its highest Mach number. Um, yes. Just give me a second. Let me think about theta. The flow has expanded. Does the flow expand even further? Let me think. The Mach number where. Okay. 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 So now there is a reason we have to define the local angle at which this um, nozzle uh, what is the slope, local slope of this nozzle? What is this? And we know that is called as theta max. And I'm going to write it as theta max. Also, ML also I'm going to write. Basically, we mean minimum length nozzle. Um, Now, how are you going to find it? What is the logic there? Just like how you see that the last C minus line expands the flow to certain manner. Okay. And then there are going to be a series of another expansions and their final expansion, that is going to happen. So if you think about it, the flow is expanding this flow, the flow which is in this part of the region, first the flow expands by a series of C minus waves and then by the flow of C plus waves. In this part of the flow, what is happening is it does not expand by all of the C minus waves, by some C minus waves and then some certain C plus waves. So a combination of C minus and C plus waves. In this region, there is only flow expansion by happening in the region of C minus waves or the left running characteristics. The disturbance, there is a disturbance only from left running right running characteristics. Then it reaches this whole region, and in this whole region, there is only expansion through right running waves. So if you think about it, so if you look at the flow at this edge, what we expect is, first of all, we expect this flow and this flow. Okay, there's also an interesting thing that only at the wall is that true, that there is a series of C minus waves and then C plus waves. You see, the ones this green line also enters this yellow line. So there's also uh, I will not call it merging, because this C minus and C, this characteristics match is our construct. But if you look at it, you see that uh, suppose so if I look at this flow, let's say some line, it teaches two lines, first two C minus lines, and then before hitting these two the third C minus line, it hits the first C plus line. Then it goes and then it expands. So it will depend on how the flow is going to happen. We'll have to see that. Like you can resolve it obviously, but the thing is that at the wall, we expect the flow to be again at the exit of the wall. We expect the flow to be exit Mach number. So the way we calculate this angle, theta max, the way we calculate theta max is we see that there's a final expansion by first C minus line and then C plus lines. And that is what we are going to use. So along these lines, you see, if I mark this as some point, you see that along this is a point along which I can write theta. So along this line, which is an uh, C minus line, so K minus is going to be constant. The constant, so theta plus nu, isn't it? Is a constant. Theta A uh, nu A is equals to, let's call it for time being, let's call this point as C, point C. Okay, so now theta C plus nu C. Now we know a little bit about theta A and theta nu is fine. What else do we know about it? Okay, and then from theta, this thing, and let's call this final point as, let's say D, or let's say B or something. Let's call this as B, and let's call this as C. So theta B and theta A are have this relation, but this is corresponding to C minus line. And then we will also use this thing. Okay, so this right running line, you see at the exit, you know theta has to be 0. So theta c has to be 0. That is what you know. And corresponding to a mu c value of mark exit, mu c also you know. Sorry, mu c. Nu c also is something that you know is equals to nu of me. So you know this value. But what you don't know, uh, again, another thing is that this B point lies on the center line. So again, we know theta B is also 0. Is also 0. That is an important thing. So what we are saying is, um, at the center line, once the C negative hits the center line, then it will reflect back and reach the nozzle exit. That is gonna happen because that is the last that is the only way. There are not. So first of all, so see what is happening in the nozzle. The sonic flow sees a sharp corner at the throat, and that is the cause of the entire expansion that is happening. All the C minus lines emerges from there. There is no other point of uh, disturbance, and then it hits the center line and so on. So basically, theta b is 0. Uh, then the center line, the flow has to be constant. What that gives you is that mu b mu b is equals to nu corresponding to me, and what that does is uh, theta a we must also, and we also know mu a also. We know mu a is 0. You know mu a is 0. Is mu a 0 or mu a? Well, mu a is not 0. See, mu a is the point. So along this C negative line, mu a is the point of flow is so see now it's important. So nu a thing is that this is a Prandtl expansion, right? What is happening at the sharp corner is that nu a theta a is something that we'll have to calculate. It's actually theta max ml that we know. But what is nu a? Nu a is actually Prandtl expansion for corresponding to this angle only. It has to be theta max ml. Why is that? So what happens then? So for that we have to write the equation for Prandtl expansion, and that is m2. So two mu m2 is equals to mu m1 plus theta, the angle of expansion. Now mu m1 is 0, so theta a, sorry, mu a is equals to theta max ml from this because mu m equals to m1 equals to 1 equals to 0, and this mu m2 is actually mu a. From there we get one important thing. What do we get? Is that we get a relation that theta, the initial theta a, we get theta a from there. Is actually uh, mu me by 2. Okay, this is something that we get. Now think about it. Uh, this point, this point, this is the point, this is the wall point. So we are saying uh, that once the flow has been expanded by all the C minus waves, and it will get reflected. It is going to expand by the reflected wave. So we have a slope for this wave also. Um, so what demarcates this point and this point? Actually, this point and this point has to be demarcated by the local slope. So this local slope, not local slope, average slope. So this point is actually demarcated by the. So we know there is a local slope associated with A, and we know that there will be a local slope associated with this point also. Let me call that point as A1. Okay, because there is going to be an expansion here also. So there will be a local slope associated with this also, this point also, isn't it? So we see that these two have to be connected by a local slope. So there will be some theta A, there will be some theta A1, and there will be an average theta A average, or let's say theta average. This point, the wall point, gets demarcated by the intersection of this line and the average slope. So let's start doing things so that we can figure things out. Okay. Um, I'm going to take a small break and then we're going to resume. Okay. Okay. So let's start coding. Let's see what to do. Okay. Um, First of all, uh, we will need a couple of things. First of all, we will also need, let me do this new thing there. We are going to need some helping functions to when we write the code. So let me just mention those helping functions. Okay. Then we are talk about other things. So there are some libraries that we use in Python these are simply libraries. This is the array library. This is a very general library. Let's look at what is meant by. NumPy is a very famous library, very basic. It has to be used. So arrays and matrices, it is used for arrays and matrices. Uh, Other mathematical functions also, it is very helpful in that sense. Um, we are also going to use some helping functions. So let me mention those helping functions. So the first helping function is the Prandtl experiment. So for a given Mach number, what is the mu value? So that I have written down. I'm not explaining that. Then comes the Mach angle. So this is the Mach angle line. Uh, Again, given a Mach number, what is your mu value? For a given theta and mu, there will be some Riemann invariants. Well, let's not call them Riemann invariants, or maybe can we call them Riemann invariants? Let us see. Are they termed as Riemann invariants or not? I don't think so. They're not Riemann invariants. Yeah, those are different. So k plus and k minus. K plus is corresponds to theta minus mu, and theta plus mu. Okay. Also the slopes that you're going to use. These are the slopes. So given a theta and mu, we want the slope dy by dx of the characteristics. This one. Yes. We are going to use this. Okay. One more thing is that for a given new value, we want to find a Mach number. For that, we're going to use this helping function of error in u. So for a given guess of new and a Mach number, we'll guess the Mach number. We'll have a new value, and we'll see how away we are from our. So guess is Mach number. New is the value that we need. New is the some value that we have. We want to guess the Mach number for this new. So for that, there's this helping function that we are going to use called as Newton. This is the Newton method. Implement the Newton method to find this function. So what we are going to do is going to use this. So this inverse Prandtl function for a given new value, you start guessing a Mach number. You give a small first guess, some value, it uses this error function. It will check how far away you are from your actual error. So it has to be 0, and it will find the root for this function, basically. So new minus this, so it will find the root for this function. It's the root finding function if we think about it. Now, another thing is that you see that we have to use this. We have to actually simulate this also. If you think about it, we have to start finding these points, right? As I mentioned, these points 1, 1, 2, 1, 3, 1, 4. There will be other points also 2, which is the second intersection of the this center line with the second characteristics, the third line, the fourth line. So we have to mark points which are intersections of two lines, maybe C minus and C plus, maybe the center line and the characteristic lines. So in that sense, we need a helping function, another helping function, which finds the intersection of two lines. Okay. And I'm gonna wait to explain its working. I'm gonna wait before I explain this. I'll go ahead and also write other few things. Okay. The next thing I'm going to write is how are we going to save our data. So I'm going to save our data also. So the way we are going to do that is going to save our data. How are we going to do the saving of this data? First of all, for a given exit Mach number, we are going to find the theta max, and that is going to correspond to Prandtl of this Mach number divided by. So that is one property that we are going to use. That will dictate one design. Then a design is, if you see the minimum length nozzle design is getting characterized by the exit Mach number. And then we have two starting points: the origin, which has x equals to 0, y equals to 0, and the throat corner, which I have taken to lie at 0, 1. So based on that length, height, that throat height, throat half height, we are going to get the all other points with respect to that point. So with respect to means, suppose your throat height is 5 meters. 5 meters is too much. Let's say 50 centimeters. Then if I divide the entire geometry by 50 centimeters, then we are going to get, so basically it's a normalization. I'm assuming that the throat height is at 0, 1. So entire shape that is going to come is, we are going to get positions normalized to this height. That is what I'm saying. And with every point, there is certain properties associated with it. There is a new value associated with it, which actually is associated. Both these points will be because they lie on the sonic line. This will be 1 and 1. Theta decides the characteristic. This, what do you call it? The streamlines angle. What is the direction of flow? And both of these points, the flow direction is essentially 0. The its flow is action. Just behind, actually, A is the point of kind of, let's say, singularity, because a lot of C minus lines are converging at that point. That in reality that does not happen, and there is no sharp corner. There is always a minimum radius associated with it. So that is why. But if we particularly speak at the very edge of the sonic line, the theta is 0. Then associated with that Mach angle, there is also mu, which is sine inverse of 1 by mu. And so we find out the Mach angle. So I should have given it as Mach angle of m, but that is fine. And then k, there will be k plus and k minus also. Again, for any given m and theta, you can find other properties. Okay. Then, so there will be a series of points which we have to plot or find based on the design Mach number. So we'll start storing these points as, so I've stored it 0, I've stored it as A. We're going to add to this list soon. But this is the initial structure that we are going to store our data in. There will be some C minus lines that we're going to store lines in the C minus section. There will be some C plus lines, we're going to store them. Then I've also ensured to store all the lines, no matter what it is, C minus or C plus, we are going to store it in lines. Just plainly, we can just combine C minus and C plus, but I want to store it in this line. I have kept it. Then nozzle stores the points. Again, yes, nozzle will store points. Okay. So the way I have kept it as nozzle, what I mean is actually it should mean wall. So I want to store the wall points. So it should be wall actually. But let it be, let me call it as nozzle. And there's also an interesting thing of how I store lines. So what does a line imply? Generally, line can be defined by a slope value and by a point to which it passes. That is how I'm going to define a line. But when we are going to plot uh, the nozzle, I also want to keep a second point so that I can plot the line between these 2 points. So although I'm going to start my line from 1 point and 1 slope value, I'm going to add to this points array so that I can have 2 points and I can plot between these 2 points. Okay. So that is something that I'm going to have. Now with this structure of line having 1 slope value and an array of points, this essentially this array of points can be at max have 2 points, or the way I have written my code can have 2 points. And based on this structure, I have written this helping function of find intersection. Now, if you think about it, I have used a finite slope value. I have to define a slope value. So essentially, my code cannot take lines of 90-degree lines. These what do you call lines parallel to y-axis? They cannot be dealt with using my code because I need a finite value for it. Uh, just give me a second. Yes, sorry, actually, this was this one important mail I had to go through, message I had to go through. Anyways, just give me a second and get back. Okay, let's continue. The way this thing works is that we are expecting the slopes to be some finite value. So slopes cannot be some infinite number. Now that slopes cannot be infinite, they can still be zero. That is another asymptotic case. In that case, you can't simply find intersection by using finite mark this slope values. So in that case, I have considered if either of the two slopes have a zero are zero, then what we do is they will have the intersection point will have the x is um, y value corresponding to either of the two lines. So both lines pass from certain points. So if there is a uh, if either of the slope is zero, the corresponding y value will be the value of the intersection also. So that is something that I have done. I find the non-zero mark slope. Then I find the pi value corresponding to the non-zero slope and zero slope. And then I calculate the x and y's, and then calculate the two x's and again find the intersection. For the non-zero y values, it's a simple thing. You find you develop a function, y function from the line one, y function from the line two. You find a root, so you develop a root finding function. So yx or y function of x minus y function of y, y function of line one and y function of line two. Subtract both of them. Start guessing for an x value, and you calculate x and y. So this is how you find the intersection. This is a helping function. You can go through it. It's a simple thing. This is one way of what I have done. Okay. Now, now let's look at the other phase of the process. There is also one more thing. So the next thing that we are going to do is the first thing that we do is it's now this is uh, a simple stuff. What I have done is so the first line which I mark is the center line. So this is marking the center line, registering the center line. So I register a center line as the first line important to our calculations. Okay, and for that I define that there is a line, uh, line zero, which has a slope zero. See here, and to that point, that line, I add the point origin to it. So it has now a slope 0 and it originates from the origin 0, 0. The next thing which I do is I put the fourth corner as in my wall, uh, in my area of wall points or nozzle points. Okay. So throat corner marks my the start of wall nozzle wall. So this is something that I do. The next thing which I do is I start calculating with the theta max. I start calculating theta max. Okay. So I will start calculating theta max. That is something that I have to do. Okay. This everything which I'm doing, let me do this, is a in a function. So let me do this in a definition design. And that will need p values. So let me explain what I'm doing. So what I'm doing is I'm designing a function, so it will need these values. Okay. So these are the first steps to it. The next step is finding theta max. Step one. Step one is immediate corner theta. So to find the Prandtl-Weyl expansion of that theta, how much theta does it expand to? Is that we find that theta max expansion. Immediate expansion. So this will give you the trailing expansion wave, the last expansion wave. There will always be a last expansion wave, right? Which expands the flow to this theta. So we will find the last expansion wave, how much we need. Based on that, we have to start. Uh, we will have to grid discretize. We'll have to find the. We'll have to do this discretization, grid characteristic grid. We have to find that characteristic mesh. Okay. For that, we use this n that defines the density of how much lines we will take for this grid or for this angle to divide how much at what angles we will divide this expansion corner. Okay. So, and again, we will need a gamma value and a exit Mach number. So maybe we'll try. What I'll do is we at the end of it we'll try how gamma affects the entirety of the design. Okay, and how it affects and so on. So let's see. So now the next thing that we will look at is, so these things are done. Okay, so now the next thing is deciding our grids. So the way I grid construction is done by selecting certain theta values for which we will start registering uh, C minus lines. So for that, what I do is I start with this line. The first theta I pick as the decimal part of it. So if suppose theta max is 13.355, so the first theta I choose at 0.355, so that the remaining 13 can be equally divided by in some n minus 1 terms. So what I do is, let's say if I have 18.75 and n is 7, so the first angle will be 0.75. Then we will have 18 divided by 6 is 3. So then 3.75, then 6.75, and 9.75, and so on. Okay, this is the intent there. So once I do this, then there is a process of registering all the C minus lines. So let's register C minus lines. So that process involves um, that process will involve uh, so, so what I do is then I move from 1 to n plus 1. And every time I move from one grid point to the next grid point, I start, first of all, I add theta in my grid, register next grid point, and then correspondingly find the C minus values of it. So across the expansion wave, what you have is you have theta. So now I write. So now corresponding to a C minus line, what else do we have? So corresponding to a C minus line across an expansion wave, what all points do we have? We do not have a we will not have x, we will have a slope for it. We will have a k minus k plus for it. We will also have a Mach number associated with it, right? We will have a mu value associated with it. So new value, and also theta value, it seems. Let me think why a theta value. Yes, so the theta value is associated with the where so it's this these C minus lines are coming from a corner, right? This throat corner, the expansion corner, right? So that is why you will have a theta value also. So what is the flow after this point? That is what it is. Okay. So with that, so now, uh, so now with every C minus line, you see the first theta is 0, okay, which corresponds to sonic line. The second theta corresponds to the first grid point, this one, which will be, let's say, 0.4, 0.75. As we start adding next points, so it runs from 1 to n plus 1. The first iteration, you need, so because you add theta, if initially you could have added theta later on, then this will make more sense. So let me change that. So if I do that, then you choose the theta which you have, this one. This is the theta by which you want the flow to be not shifted, I should say rotated by. So you will have a theta for this. Now, what will the nu correspond to? Because again, now here we are using, actually, you see the Prandtl expansion formula. Nu2 is nu1 plus theta. So nu2 will be actually point A, the Mach number at point A, which is 0. Which is 0, right? Point A corresponds to a new value of Mach value of 1. So for which it is 0. So we can simply, I could have simply written down nu equals to theta. Okay. Now this thing, once this is done, um, this is fine. So now using theta and nu values, now we can always have k plus and k minus values that we will give. We will find Mach number also. We'll find mu values also, and so on. This is simple. One more thing that we will do is now, because C minus lines are lines which originate from A, and they have a slope. So we are going to use these slope values. And how are we going to find that slope? So we know that C minus have a slope, tan theta minus mu. So you have theta and mu, so you will get a slope from this helping function, which we wrote down earlier. So it has a slope, and that slope we are going to add as a line. So in our code, every time I write a C minus or C plus line, I will add it as a line. That is this append function. What it does is it adds it as a line. So it has a slope, and the point is A. So every time, so all C minus lines are registered at this point. In this, once the code runs, at the end of this loop, all C minus lines would have run. Again, now what we'll do is, because we have all C minus lines, we'll first find uh, the point at which it intersects with the center line. Then, so let's do that in a sequential way. So once I do this, what I'm going to do is I'm going to run another for loop. So then you see, okay, at the point of, so now the intent is, let me write this, registering C minus lines, right? Okay, now what you're going to do is registering intersections with center line. See, um, there is a inconsistency in our method of characteristics, the way we have been solving things, and it is actually mentioned here. So note that a small inconsistency is involved with the properties at the first. So point one is the point at which the first characteristic line will intersect with the center line. Uh, we get a value of theta. We give a finite value of theta to point one. See, theta is given at some finite value, but at the center line, theta has to be zero. It cannot be some finite value. This is inconsistency is due to the necessity for starting the calculation with straight characteristic line A1. So you see, you actually need a line to start the calculation. The flow has to be expanded, and that characteristic line has to hit somewhere. It will get curved actually. So the thing is, so actually let's read this. Uh, Along which the value of, so this is due to the necessity of starting the calculation along a straight line A1, along which the value of theta is constant and equal to 0.375. In reality, the characteristic A1 is curved because of non-uniform flow inside the region AB1. So what is the region AB1? In this region, there is a non-uniform flow. So A1 will be a little curved. It will not be just simply a straight line. And so it will be curved in the sense that here it will be straight line as theta will be 0.375. But in this region, theta will become 0. But we will avoid this inconsistency. But we have no way of knowing what non-uniform flow is there for this problem. And we must live with this inconsistency. So what we do is, in order to start this calculation, for the first line, we assume theta to be equal to, because we know information about this region. See, in this region, just behind this first characteristic line, we know theta equals to nu. So we are going to employ that information here itself to even start this calculation. It is a little inconsistent and it does not give, and we don't have a very strong justification also as to how can we do it. But let's live with it for a while, and we'll not worry too much, because if this that is why this angle has been taken as a very small value. The smaller the value you take, the more accurate you will get, right? Theta has to be smaller. So that is something that we could do. So let's not discuss what are the implications, how wrong we are, and so on. Let's say this is the method that we do, because we are simply I'm just demonstrating this method, right, numerically. So for that purpose, what I'm going to do is, the next first thing that we do is we assume theta to be 0 generally if I is not 1, but otherwise you take the theta corresponding to this C minus value. So you see theta of this thing, you take this value, okay, just behind the first C minus line. Otherwise, you take 0. Now, how do you find the intersection points? Okay, so let's go back. See, the way you find intersection points is along a C minus line, K minus is a constant. Along the center line, theta is a constant. Theta is 0. Um, so we use that property. Okay, we use that. So we say, first of all, that C minus line, we find out K minus value. Nu we find out as K minus minus theta. Theta we give at 0. Okay. So nu at that point, at the point of intersection, we'll calculate using K minus minus theta. K plus again, then we will calculate what is K plus. K plus will be theta minus nu. What we could have done, where we could have had done is use this rather than using this. This is, isn't it? Right. Then, then we find the Mach number using this functions, helping functions, mu value we find out, and then we find out the point of intersection between two lines. Okay, the first line is the center line, which is dictation, the first line, which is the center line, which we have saved it as the first line, and the nth line. You see, we had been storing the C minus slopes uh, as these, right? In this, I could use actually C minus 1 C minus 1. I would have to use C minus 1, I minus 1, but let's avoid that. Line, this is the uh, C minus line only, right? So corresponding to the C minus line, whatever C, you are at the first C minus line or the second C minus line, you find the intersection to it. Okay. And then you start storing that point also. So whenever you find a point, I store it in my points. Okay. And I store it with a name. So the name I store it with is give it as a name as one. Sorry, I. So the way it will work is, as I discussed here, this will be point one. The second will be point two. This will be point three. This will be point four. Okay. So this is how I move. This is my nomenclature I have used. Okay. Uh, Now what I do is, um, okay, as you move along, uh, actually I don't need to do this. Um, I can just simply do this. I'm changing a little bit of my code. What I was doing is, once I reach the end of my lines, my C minus line, I will define it as the point at which the last thing. So you see, if I open that up in my code, because I'm rewriting the code for you, right? You're rewriting. So the way it works is that once I plot my line, I plot it only up till the point of the last point at which last characteristic line uh, intersects with the x-axis. Okay, so this is why I've done it. What I have done is, once you are at the last characteristic line, um, the first line store the second point. So I told you, right? Once I plot lines, I need 2 points. So I store the second point as the point of intersection of the last line. Okay, maybe I'll remove this, or let's not remove it. For let's see if my code fails or anything in that manner. Then you also find the slope of okay, for the given theta and mu, there is a slope which is this. There is a, now what is this? Up till now, this is all fine. Now uh, we start looking at C plus line characteristic originating from this point. Okay, we find the slope of this line, whatever this line is, and we store this line. We find a slope for this line, C plus line, store a slope for it, and we know that this whatever the last point is, the point we have found out recently is the point at which it originates. Okay, so we use that. Then the next thing that we do is, now this C plus line will intersect with the rest of the C minus lines. Now I'll show you. You see, in this sequence, the first C plus line intersects with, it originates from the first C minus line and it intersects with all the rest of the C minus lines. Similarly, because the second C plus line cannot intersect with the first C minus line. It intersects only with the rest of the C minus lines. So you see that once you have stumbled upon the C plus line, you have to go from the next C minus. So to find the points of these intersections, you have to see the intersections of the next this line with the other next C minus lines. So for that purpose, we write a inner loop of this manner. Very simple, nothing very fancy. We write a simple code, a simple for loop. Every time, the idea is every time you stumble upon a C plus line, find intersections with rest of the following C minus lines. Okay. So again, along this C plus line, K plus is given, is known. And so we use this. And along whatever C minus that we are interested in, we are at the ith C K plus line. So let me mark that. K plus of ith C plus characteristic. The way we go into that mesh of C plus and C minus line is this way, and K minus of jth C minus characteristic. Okay, using that we find theta and nu, we find Mach number, mu, and x and y. Again, how we find it by the I should write it as okay. So okay, so something which I did not do here, let me do this. See, what I have done here is I have done this, right? I should do it this way. C plus dot append so C plus I don't know if I will be able to write this. So actually, basically, this intersection is here. Let's forget about this. Intersection is the last line. What is the last line that we have instruct this thing? This is the, let me mark this. The last line is the recent C plus and the jth line. Now, what is the jth line? Jth line corresponds to the line of jth characteristic, right? You see here, this was the jth characteristic, right? Right? So that is how that we have done. This is the logic. Once I do this, I'll stumble upon a point, I'll store that point. Now, what is the next step? Nothing much. Now we have stumbled, now we have intersect, now we are at the end of again. Now we have to just find the wall. Okay. So in order to find the wall, what we do is we find this. So we find so theta, now we have to find the average slope. As I told you, I have to find the average slope. I will be somewhere in the I will be now I am at now I am stumbling upon some ith C plus line. So I have to find a corresponding wall point at which the C plus line meets the wall point. So I have to find the point at which this wall point uh, and that wall point is actually found out by intersection of the recent slope, the last nozzle point, the slope at the last nozzle point, and the local slope of the C plus line. So what we do is we find the last theta value. So the wall point is found by the last wall point and what? So let me write that. Slope of last point. And what is this? Okay. This is theta 2. This is what it is. Okay, this is the local slope. Okay. Could have used this theta also times. That is why. So what I've done is I've used the theta of the last intersecting point. So either this, if I is less than n, or half of it. One more thing is that see the last characteristic line. The problem is with my code. The way I have done it is this is actually problematic. It's a small fix there. It should be the last. It should be the recent theta, and that is what it is. You can forget about this thing. You can forget about that. It should actually be a plus, and that's okay. So then we find the local slopes and then we average it out, calculate the intersecting point, save it, save all the nozzle points, and that's it. We are done. Okay. So now with that, let's return dictionary. That's that's it. That is what you're going to do. Now, dictionary one is design. What is the issue? Okay. So actually I should give gamma. Maybe I can give gamma as a this thing as a global variable. Let me give gamma as a local global variable. Now let's change gamma to 1.67 and do the same thing. And let's see what happens. So we are finding a mark, design mark number is our for our this thing is taken default value of 2.4. So let's plot this thing. So plotting function you can just see. I'm not gonna spend time on this one because we are almost out of time. So let's one thing that we can see is see dictionary 2 has a gamma value of 0.7, so that nozzle length has decreased. And if you see, the height has also decreased. For a lower gamma, the height is increasing. So if I want to plot it, yeah, I don't know if I will be able to see it or not. See, you can change the colors. Maybe, yeah. Okay. See, this is how it looks. That's how the colors change. Okay. Shape changes, right? Theta max is same, but gamma value, you see that there is a change in the final loss. Then similarly again, let's do this. Not because of this thing. Let's not because of. Let's look at mark exit of 2, and let's look at mark exit of 3 or mark 0.4. And because of higher extension requirement, it will be longer. It will be longer. Interesting, right? You can start plotting, you can plot these things. And that is how you can solve this thing. Okay. But this is something that I wanted to describe. We'll stop the session for now and see you later on. So nice to interact, nice to have interacted with you guys. And you can always reach me out. Maybe I'll open this introduction thing for one last time. I am Shrey. You can always reach me out before your exams or anything. And see you soon. Maybe. Yeah. Bye.